Welcome to the SAR channel, where sound and audio are demystified. Music is an acoustic event. Whether it comes from a musical instrument or an electrical signal, it needs air to travel and reach our ears. Acoustics is the science of sound. It studies how sound is produced, transmitted, and received. When a bow moves across a violin's strings, the strings vibrate, compressing and expanding the air around them. This disturbance in the air creates the sound we hear from the violin. Sound travels through air by the motion of air molecules. These molecules bump into each other, passing along the energy of the vibration. This means sound moves as a series of local disturbances spreading outward. The air molecules move back and forth in the same direction as the sound wave, so sound travels in a longitudinal way. If something like a microphone diaphragm is placed in this sound field, it vibrates according to the air pressure it receives. A transducer is a device that converts one form of energy into another. A violin is a transducer because it turns the bow's mechanical energy into sound energy. A microphone converts sound energy into electrical energy, while a loudspeaker does the opposite. It turns electrical energy back into sound. Sound vibrations can be periodic or non-periodic. A violin produces periodic vibrations, while a cymbal produces irregular, non-periodic ones. A single repetition of a periodic vibration is called a cycle. The number of cycles per second is the frequency, measured in hertz. The time for one cycle to complete is the period. Humans generally hear sounds between 20 Hz and 20 kHz, so most audio equipment is designed for that range, though digital devices can handle higher frequencies. The wavelength is the distance a sound wave travels during one cycle. Because the speed of sound in air is nearly constant, about 343 meters per second, wavelength equals speed divided by frequency. For example, a 20 Hz sound has a wavelength of about 17 meters, while a 20 kHz sound has one of about 1.7 centimeters. Most transducers, including our ears, cannot handle all wavelengths equally. Their frequency response is limited. The difference between the lowest and highest frequencies a system can reproduce is its bandwidth. Two waves that rise and fall together are said to be in phase. If they move oppositely, they're out of phase. The difference in timing between them is a phase shift, and when out-of-phase waves mix, they create new sounds through constructive or destructive interference. When sound moves around barriers or through openings, it bends, a process called diffraction. The longer the wavelength, the more it bends. High frequencies, shorter wavelengths are more directional. Try holding a magazine in front of a speaker. The high tones are blocked while the low ones bend around it. Sound can also refract, or bend, when its speed changes, such as with temperature shifts. It bends away from warm air and toward cooler air. The speed of sound in air increases about 1.1 feet per second for every 1 degree Fahrenheit rise in temperature. Sound travels at different speeds in different materials. It moves faster in more elastic and less dense media. For instance, it moves about 14 times faster in steel than in air. As sound travels, it loses energy. This is called attenuation. High frequencies fade more quickly in air. Also, humidity affects sound. Moist air absorbs sound more, but lets it travel faster because it's less dense than dry air. Amplitude refers to how much sound pressure moves above or below normal air pressure. Sound pressure itself is very small. For example, if the normal air pressure is 14.7 pounds per square inch, even a loud sound only changes it slightly, between about 14.699 and 14.701 psi. Still, the difference between the quietest and loudest sounds we can hear is enormous. The human ear and most audio systems can handle a dynamic range of about 1 million to 1. Because this range is so large, we measure sound pressure level, SPL, using a logarithmic scale called the decibel, which is based on powers of 10. The reference point for measuring sound pressure is an incredibly small pressure of 0.0002 dyne per centimeter squared, which represents the threshold of hearing or the faintest sound a person can detect. This is set as 0 decibels SPL. The threshold of discomfort, where sound starts to feel painfully loud, is around 120 decibels SPL. It's important to remember that decibels don't add up in a straight line, because the scale is logarithmic. For instance, two sounds at 50 decibels combined don't make 100 decibels, but only about 53 decibels. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. Okay, let's continue. The simplest type of repeating motion is the sine wave, created by basic oscillators like pendulums or tuning forks. A sine wave contains only one tone, called the fundamental frequency. All other repeating waveforms are complex, made up of this fundamental tone plus additional tones that are multiples of it. For example, if the main frequency is 100 Hz, a complex sound might also include tones at 200, 300, 400, and 500 Hz. These extra tones, called overtones, sit above the fundamental. The strength and timing, amplitude and phase of these overtones shape the timbre of the sound. That's why instruments like a piano and a violin can play the same note yet sound very different. Their harmonic content isn't the same. Our ears can't easily sense very high overtones. For example, overtones between 10 kHz and 20 kHz are hard for most people to hear. Still, to accurately record a sound, both its fundamental tone and harmonic structure must be captured within the audible range. According to Fourier's theorem, any complex repeating sound can be broken down into a series of sine waves at different harmonics. Likewise, complex sounds can be built by adding sine waves together. Using a mathematical transform, a waveform in time can be converted into a frequency-based representation. For example, a square wave can be broken into one main sine wave plus higher odd harmonics. The inverse transform does the opposite, turning frequency data back into a time waveform. This principle applies to digital audio too. Some systems, like CDs, store audio as time-based samples, while others, like MP3s, store it as frequency data. Because real sound is extremely complex, even the most advanced analog or digital systems can only approximate reality. The sound we hear through them is always just a close representation of the original. Analog sound and audio systems work with continuous signals that change smoothly over time, while digital audio deals with separate, step-by-step values. In digital form, the height or amplitude of a sound wave is represented by a series of numbers. This means digital audio is a numerical method of capturing and processing sound. While humans use the base 10 system, numbers 0 to 9, digital computers and audio devices work more efficiently with the base 2, or binary system. This system only needs two states to show whether an electrical signal is on or off, represented by 0 and 1, called bits. To process any kind of information, such as turning an audio signal into digital form, a digital processor converts it into binary numbers. Figuring out how to accurately encode sound into binary is one of the main challenges in digital audio design and operation. If you have learned anything new so far, please like the video. It really helps the channel grow. Thank you. A decimal number can be directly changed into its binary equivalent, where each binary value represents a decimal number. However, there is a limit to how many values can be stored. An n-bit binary number can represent 2 to the power of n different values. For example, 2 bits can represent 4 combinations, 000, 001, 010, and 011, which correspond to the decimal numbers 0, 1, 2, 3. The binary number system makes it possible to design powerful electronic hardware and software. Boolean algebra is a method for combining and controlling binary signals. It is essential in digital systems because it allows for decision-making, condition testing, and logical operations using only the digits 0 and 1, along with operators like not, and or, and a set of logical rules. Imagine two identical containers, one filled with water and the other with beads. Both completely fill their containers, but the way we measure them is different. With water, we can weigh it or use a measuring cup, but we might spill some or leave a little behind, making our measurement less accurate. With beads, we can simply count them, and that count gives a precise measurement. The beads represent discrete values, like in a digital system, showing how digital methods give more accurate and repeatable results than analog ones. Measuring 1,000 milliliters of water is harder and less exact than counting 1,000 beads. Measuring requires special tools, while counting can be done anywhere. A digital system is simpler conceptually, since it just counts numbers instead of tracking a continuous flow. Processing data representations is easier than handling the original continuous signal, though the technology behind digital systems is more advanced than analog gear. In an analog chain, from recording to playback, the signal is continuous and passes through many circuits that each add distortion and noise, causing signal degradation. Analog devices are also large, power-hungry, and less reliable. In digital audio, the analog sound is converted into binary data, processed and stored digitally, and only turned back into analog at playback. This avoids most analog distortions. Digital systems are cheaper, more durable, less noisy, and more flexible, allowing software algorithms to process sound with great accuracy. Although digital audio avoids many analog flaws, it still has its own unique challenges. Thank you for watching till the end. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.